Okay, recording is started. We're going to be talking about problem solving in the quant section today with flexible approaches. We have already done the intro and the rules and so on and so forth. And what we're going to do is hammers in that problem. Again, just in case you just got into the room, I'm teaching an online class on Wednesdays, these dates, these times. This is Pacific U.S. time, Eastern U.S. time, and Indian Standard Time. If you're in another time zone, I know most of the time zones off the top of my head, but you can chat box it if you want. But that's when there's going to be an online class. All right, let's take a look at some problems. And again, the usual disclaimer, these problems are all from the GMAT prep software unless we note otherwise. Okay, how about something like this? And again, remember where your multiple choice answers are found, please. Multiple choice answers are found underneath your name in the box that looks like a little letter A. Okay, it's been a couple of minutes. If any of you guys have not finished the problem, please guess something. Remember the way this problem works, remember the way this test works, is you have to pick something. You can't not pick something. If you don't know the way the test logistics work, they wait until you sit there and they sit there and wait until you pick an answer to it. So, all right, let's pick something and talk about it. All right, so remember what today's theme is. What today's theme is flexibility in problem solving. So what we're trying to do today, in other words, is approach these problems from multiple angles, some of which are consistent techniques that you should have at your fingertips, and some of which are things that you just might not have thought about at whatever point. So, okay, this is a probability question. What we'll do is we'll take a look at this by traditional means in a second. But let's talk about how you guys first ever learned about probability. Like when you were in grade school, long time ago, you probably learned probability as a function of something like dice or a spinner or picking a number from 1 to 10 or something like that. How did you first learn probability when you were first exposed to it? Chat box. Like how are you taught that it was a thing? What was your first introduction to it? I know you're red and blue balls, dice, but how were you introduced to the notion of calculating it? Like how did they teach you how to calculate it? You desired over total, as Zach is saying. But how did you get these quantities called desired and total? So Zach says here. I mean, you've learned a lot of fancy things about probability since then, but this is how you first learned it. In other words, how'd you get those? Yeah, you count them. And I mean, the thing with probability on the GMAT is that in most of the problems on the test, this is still an available option. You can just count the number of desired options and count the number of total options and just see what those two numbers are and just divide them. So let's do that here. Very, very much doable in the time that you have. Very doable. Let's take a look. So you have 6 workers. You have Joshua, you have Jose, and you have 2 other people. So it's 4 other workers. In other words, this is the fancy way of saying you have a total of 6 workers at the center. Okay, so let's list all of the ways. So let's just say we have workers numbers 1 through 6. I mean, if we're going to make a list of these things, we want to be efficient about it. So, I mean, 2 of them are named Joshua and Jose, but we'll just number those guys later. Because it's easier to make lists of things that are numbers. So let's say the workers are numbers 1 through 6, and let's just list all the ways we can pick 2 of them. So notice that order doesn't matter here. So you don't need to list 1 and 2 and also 2 and 1. So here are some ways. Well, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. 2 and everybody else. Notice we don't need 2 and 1 because that's already been done. 3 and 4, 3 and 5, 3 and 6. 4 and 5, 4 and 6. And finally, 5 and 6. Okay, the point that I want to make about this list, the first point is that it is a thing and you can do it. The second point, which is probably the more important one, is because most people don't do this, and the reason they don't do it is they just don't want to. But what they say is, oh, I don't think I'll have time. And what I want to point out here is if you say, I don't think I have time to do this, you're wrong. I mean, this is not a very long list. It's really not. You can just make the list. It's only got, let's count them, 5, 9, 12, 14, 15. There's only 15 things in this list. I mean, you should be able to make this list very quickly. I would say make it between 15 and 20 seconds. If it's slower than that, you should probably work on making lists. As basic as that skill is, you should build it. But there are 15 things in the list. And now let's just say that Joshua happens to be worker number 1. And Jose happens to be worker number 2. So the probability that both of them will be chosen is just that one possibility. This is the only instance in which both of them are chosen. So in other words, in terms of our desired and our total, this is the only desired outcome in the list. So using the fraction that Zach described up there, desired possibilities over total possibilities, and that is 1 out of 15. Not bad. It's a thing. You can do it. So the name of the game is flexible problem solving, and I mean, only about half of you guys got this problem correct, which means that the other half of you could have just made a list. And I mean, again, if you didn't think about doing this, there's a couple of reasons why you may not have thought about it. But what you should do is you should introspect a little bit about why you didn't think about it. Because, I mean, there are a number of reasons. It might be just that you're so used to taking more mathematical approaches to this that you just wouldn't think about it. But it might also be that you thought about it and then decided against it for some reason. And I mean, the reason, if you did do that, frankly, most of the reasons people decide against it are not good reasons. Like, most of them are things like, oh, I wouldn't have gotten credit for that in school. Or, oh, I just don't think that feels childish to me. Like, there's silly reasons like that. They're not good reasons. So the point is that it's something that solves the problem, and everything that solves the problem solves the problem. So don't be afraid to count things. It's a thing. Any questions about this approach? I mean, you could have, and what we're going to look at now is the more traditional mathematical approach to probability. But the point of this session in general is to put more ways of doing the problem in your head. So the point is to, oh, hey, I didn't think of doing that, or I wrongly thought that I didn't have time. So we're going to look at the mathematical approach now, but the point is to put this in people's heads. So how would you find all of them without listing them? If you wanted to literally find them all, you would have to list them. But if you wanted to find how many there were, then that would be a different story. But we'll get there. I mean, if Fred, you have to get that from context. I mean, you have to just say 2 of them will be chosen to be interviewed. So just asking yourself, does it matter, right? If you choose people number 1 and 2, if you choose Joshua and Jose to be interviewed, ask yourself whether that's different from choosing Jose and Joshua to be interviewed. I mean, it's not different. It's common sense decision, right? So that's why you don't have to count it again. I mean, even if Fred, in that case, even if you did say those were different, you would actually still get the same answer. Because you would just get a list with 30 things in it. You would get these and then backwards all of these too. You would have 30 things in your list. And then 2 of them would be highlighted. So you would actually still get away with that. Because it would be 2 out of 30. So, and more generally, if you're doing probability, then if you think order matters when it doesn't, you'll still get away with it, but not if you have to count the number of options. Okay, let's take a look at a more mathematical approach to this. But again, the main thing here is to make sure you come away from this realizing that counting stuff is a thing. Okay, because this is a session on alternative methods, we're going to spend proportionally less time on traditional approaches. So I'm just going to run through the traditional approaches when they are things, but let's try not to spend too much time on them. So if you have any sort of AND situation with probability, then you're going to be multiplying probabilities. So, and the thing you have to know about multiplying probabilities is that when you multiply together probabilities, the order is always taken into account. It's never disregarded. The order is always taken into account. And so what that means that if something can happen in more than one different order, then you have to take all of those orders separately into account. So you have to count for all of those orders separately. So what we're doing here is you can pick Joshua and Jose. There's 2 different orders in which you can pick those. So you have to consider those 2 orders separately from each other. So you can pick Joshua, then Jose. Or you can pick Jose, then Joshua. Either way, the probability of picking Joshua first is 1 out of 6. The probability of picking Jose after you have already chosen Joshua is 1 out of the remaining 5. So that's 1 out of 30. And then the probability of picking Jose first and then Joshua is the same. You're starting again 1 out of 6 followed by 1 out of 5. So if you combine these with each other, then you're going to get 2 out of 30, which is 115. What's interesting about this is that 1 out of 30 is not an incorrect answer choice. That actually very much surprised me, because a lot of people are looking for 1 out of 30 here, so it would be a good wrong answer choice. But it's not there, so well. Okay, there's your more traditional approach. And there are a bunch of other ways to do this that use remixes of the whole traditional idea, but in some way, shape, or form, it's going to look like that. So, again, if you just got here, the theme of today's lesson is flexible problem solving, where you use more than one lesson, or more than one method to solve the problem. So we first solved this problem by just listing out possibilities, and you should not be afraid to do that. anagram method is, to be honest, I would have to remind myself how that works, because that's another method the books use that you can also use by doing things like multiplying and adding, but that's not for probability. It's actually for combinatorial problems. So you wouldn't generally use that to count, to do probability questions. Okay, again, this is not a lesson about traditional mathematical solutions, so let's try not to get off track with those kinds of things too much. Okay, how about this problem? Give that a shot. Okay, ladies and gentlemen, if you are not picking an answer, then please pick one soon. Do you mean NL? Do you mean that you're shocked by the question or by something else? I mean, basically, you guys are, as a group, you guys are basically guessing on this problem, because as a group, your answers are very vision first. I don't know what you mean by that. Perhaps you can elaborate. Basically, the whole group is more or less guessing here. Your answers are quite evenly distributed. Okay, there are still a bunch of you who don't have answers to this. So pick something. Guess. Make a guess. All right, so remember what today's theme is. Today's theme is solving problems in different ways. Okay, and as you may remember from the last problem, some of those ways are not going to be things that are fancy. Okay, like this problem that we did last time, we just did by counting stuff. Does anybody know what I'm going to talk about doing here? I mean, the answer is going to be very close to 0, yeah, because, well, these are all very close to 0. So estimating this is not really going to work, because if you estimated this, your estimate would probably be 1 over 1 minus 1 over 1, which I'm going to estimate this as 0. If there were any choices that were not small decimals, then you could eliminate them, but unfortunately there are not. So, does anybody know how else you can do this problem? Apparently people are not thinking of doing this. You count the powers of 10. Maybe you could elaborate on that. But I'm looking for something. I mean, let's talk about how Ron would do this problem. I mean, there are fancy tricks that do this problem, and we're going to talk about those eventually soon enough. But I'll tell you how I would do this problem in a second, but let's see if you guys can guess it. I mean, because I would do this problem right here by just counting things. That's how I'd do it. I would just list stuff and I would look at the list. So I wouldn't use my psychic powers because those are not very good, and I wouldn't really factor anything out. Although the first step you might think of as factoring, but not so much. Let's go back to the problem. Here's the problem again. Okay. Nobody. Nobody knows what I would do. You guys are going to smack yourselves in the head. Okay, Angelica, that's the first step. So let's get rid of the decimals. So if you don't know that you can do this, flashcard or whatever, but you can move the decimals together, which is the equivalent of multiplying by 10 a bunch of times. So we can rephrase this as 9999.9999 over 1.00 or over 10,001 minus 999.9991 over someone's analogy. Someone's been watching a lot of critical reasoning, right? You guys are still trying to be too smart for me. Here's another hint. The way that I could do this, I could still have done when I was in like 5th grade. It would have worked. What is it? Let's see. You can do. I mean, you could do an analog of it. Actually, let me hang on to that, and I'll come. And I actually like that idea a lot. You can do that, and it will give you some sort of insight. But you guys are still trying to be way too fancy. Way too fancy. You can't, Peter, there's not two sides. I mean, there's nothing to cross-multiply because you don't have an equal. This is not an equation. I mean, you can't cross-multiply a difference between two fractions. You can only cross-multiply. If you had one fraction equal to another fraction, you can cross-multiply it. But this is just an expression. You can't. There's nothing to cross-multiply here. Now, you guys are still trying to be too fancy. I mean, I'm gonna give the game away here in a second, but you guys are all trying to be way too smart for Rod. All right, Bernier, you're getting the closest of anybody here. But okay, let me say again what I said before. I mean, I could have done this method in 5th grade. I mean, what's the only way you really would know how to handle something like this in 5th grade? Right, we're talking like 10, 11 years old here. Unicorn wins the prize. There we go. You can just do long division. I mean, that is exactly how I would do this problem if I saw it on the GMAT. And I mean, again, what you have to not do on this test is the following. I mean, see, you guys are already doing it. Oh, that's a major pain. I don't think I will have time to do that. Let me talk myself out of doing it because, gosh, I might succeed. Don't do it. Never, ever, ever, ever have that thought. I think this will take too long. Do not ever think this. Don't do it. It will destroy your success. Do not have this thought. I mean, what you should do is just do something. And if it doesn't work, you can always quit. I mean, you are not locked in. You are not locked into the method that you are trying. If it takes too long, I mean, just do it. And then if it takes too long, just quit. There's no commitment here. And then also, I mean, the more important point here, the funny thing is that the people who say that, oh, I think it will take too long, the people who say, oh, I think it will take too long, are always the people who don't have any other method in mind. And that's what's weird about it. I mean, more importantly, if you can't think of anything else to do, what are you going to do? I mean, that's the point. I mean, this is a stupid enough point, but like a lot of people would rather, like someone is saying, skip the question. A lot of people would rather skip the question than try something that might work. And just think about that for a second. You would rather skip a problem than try something that might work. Does that seem like a very salubrious approach to you? Probably not. That's not really the way you win this game. So, I mean, because if you look at this, I mean, these numbers, these are very, very, very nice numbers to divide by. I mean, think about dividing by 10,001. I mean, the multiples of that are 20,002, 30,003, 40. I mean, this is as nice as it's going to get. I mean, that's the nicest 5-digit number ever. So let's just say the heck with it. Let's just do the division. So, 999.9999. Let's do the long division. No one's going to get hurt here, right? So it doesn't go into that. So there's your decimal point. How many times does it go into 99999? Well, it goes in 9 times. That's just a 9, not a 1. Okay. I mean, look how nice this is. All you got to do is start doing it, and you will realize that it is very, very nice. 90009. I mean, wow, this is not going to be hard at all. 9990999. Okay, that goes in 9 more times. In fact, this is so doable that I can do it on this awkward online screen still within a couple of minutes. Just, if you talk yourself out of doing this, there's a lesson to be had here. Okay, that goes in 9 times. Again, 9009. Yay for Los Angeles zip codes. And then finally it goes in 9 more times. And wow, that was extremely painless. No anesthesia required. Okay, let's do the other one. 1003 into 9999991. All right, well, this is still a very nice number to divide by, so it doesn't go into the front number. It goes into that 9 times, which would be 90027. If you subtract that out, that's 9972991. Still goes in 9 times. That's going to be 90027 again. So 9700291. That goes in 9 more times. 90027. Nothing 70021. And wow, that is convenient. That's our friend. So done about that. So this is actually just 0.9999 minus 0.9997. And that is so doable that I can do it on this awkward online screen in still less than the average time it takes to get a GMAT problem. So there's a lesson to be had there. I mean, so this is 0.0002. There's only one choice that is 2 times anything, so I guess it's D boy. I guess it's D dog, rather. We're done about that. So the point is, like, if you guys were talking yourself out of doing this, then, oops, bad idea. Don't talk yourself out of it. I mean, this is not a unique incident. All right, so does anybody have an answer? Does anybody know what my answer is going to be to the question that is up on the board right now in the top corner from user C? I mean, it's not a very smart answer, but it's an effective answer. It's not as fancy as what you might be looking for. Yeah, I mean, it was basically what Yan is saying, right? I mean, in fact, my answer to this question is already on the board. My answer to this question is basically this. So if you combine the denominator, how would you combine the denominator? Okay. Well, assuming 0.9999 equals 1, well, you can't do that. You can't assume that 0.9999 is 1. If that works, you're probably just getting lucky with that. So, but just appreciate this. I mean, let me just tell you what the situation here is again. The situation is we have about 50 people in here right now. 50 people, and it took solidly 5 minutes for anyone to just come up with the idea of doing this the 5th grade way. There's a lesson to be had there, and I think you know what it is. But you just do this. You could also try to do you could do the least common multiple, which would be the product of these two numbers, which would be sort of annoying, but it could be done. And you may want to try that at home too. But don't talk yourself out of doing things, even if they are elementary and sort of pick up the shovel and dig kind of methods. There's a lot of picking up the shovel. There's a lot of picking up the shovel and digging on the GMAT. There's a lot of it. It's that kind of test. And just make sure you understand this too, because on the vast majority of problems like this, and this problem is not a weird exception to anything. Like on most problems like this, GMAT specifically engineers the problem so that pick up the shovel and dig can be done in a reasonable period of time. The problems are actually engineered like that. When you think about it, they easily could have chosen these numbers so that long division would be much more obnoxious than it is. But they pick numbers so that that's not true. Does Manhattan GMAT teach you that? I don't teach that. I can't speak for everyone else who teaches for us, but the point of the course is just to give you other ways to do it, not to discourage you from doing things. But I would never discourage a student from doing anything if it would work. I think that would be rather silly. I mean, it tries to encourage you to do other things as well. Yeah, it tries to put more things in your pocket. But putting more things in your pocket doesn't mean you have to take out the things that are already in your pocket. I guess that's what I would say. So, yeah, I mean, everything you've got in your bag, man, you can use it. I mean, you have to fish around in your pocket for a while, but you get it. Okay. All right, let's talk about fancy tricks here for just a second. I mean, to be perfectly honest with you guys, the fancy trick I'm looking at now, I would not come up with in real time. You know, I mean, I would just do the division and suck it up. But you can do fancy tricks with exponents. So, like, basically, you're not doing this totally cold. I mean, you can see exponents in all the choices. And so you might think to yourself, how can I get exponents in the original expression, which is currently not in terms of exponents? So, well, okay, 0.9999999 is 1 minus that. So if you think about it, that's got 8 places, so that is 1 minus 10 to the minus 8. So what you're going to see is I'm going to be importing these expressions from my equation editor, so it might take a second for it to show up. So that is 1 minus 10 to the minus 8. And then 0.9999991 is going to be the same thing except for there's a 9 there again. So that is going to be 1 minus 9 times 10 to the 8. So yeah, and you'll see this pop up on your screen momentarily. That's a screen cap. These things are important. So that's that one. And if you do this, the same thing with the bottoms of these, you can also do those with 1 plus things. So at the end of the day, what you're going to get is going to be something, again, it's going to take me about 10 or 15 seconds to put it together and then import it onto the screen. So thanks for your patience with that. But it's going to be 1 minus. It's going to be 1 minus a bunch of stuff on the top, and it's going to be 1 plus a bunch of stuff on the bottom. So almost there. You'll see it on your screen in about 5 seconds from now. Just have to import it here. Okay, so if you convert this whole thing into, I mean, doing this on a computer is not fun, as you imagine all these negative exponent things. So if you do that out with these fancy tricks, the entire expression looks like this. Now, does anybody notice a pattern here? I mean, the short answer to what level problem is you don't care. All right, we can get that in a sec. Does anybody see what you can do from there? What sort of relationship does? I mean, you're going to use exponent rules, yeah. This is the square of this, yeah. Perfect squares, this is, if you square this, then you get that. So this is basically just a really, really obnoxious way of using this whole idea that a squared minus b squared is a minus b times a plus b. That's basically just that. So what you're doing here, you can actually factor the top into the bottom thing times the bottom thing with a plus sign. If that sounds like nonsense, it's going to be posted up there in a second. Again, like I said, this is absolutely not how I would do this problem. I would just suck it up and do long division. But this is also a viable approach. And again, some of you guys may not have even had long division in your mental list of possibilities until today. It happens. It's a thing. So let's look at this. So here you'll see this pop up in just a second. Which is very annoying. Okay. 5 or 10 seconds, you'll see the factored expression pop up on the screen. Okay. Nobody's favorite thing in the world, but let me know when you guys see it. Needless to say, doing this with a pen and paper would take much less time. But it's still very annoying and horrible. So the point is that this is, you're just doing this. I mean, it looks scarier than it is. It looks very scary. But it's not so much, right? It's like if it's this and that, just think of it as this and that. It only looks weird because I have to use so many brackets to write it out. But it's basically just 1 plus this times 1 minus this over 1 plus this. And then this is really just 1 plus that. 1 minus that. And then if you just think of it as this and that, then it's a lot less scary. So if you do this, then they cancel. These are gone right here, and then these are also gone. And you're left with the difference of this. So it's 1 minus 10 to the minus 4th. The 1s are gone. And then it's minus this plus that, because it's minus a minus. And there you go. right? So this is doable. I mean, if you notice the pattern, it is kind of a crazy looking thing on paper. But it's really just that pattern of a squared minus b squared thing. And you cancel those, but just don't forget, or if you didn't, either don't forget or just make sure you are aware in the first place that that's also an option. You can just do long division. It's your friend thing. You can do it. Okay, the short answer to the difficulty question is you don't care because you won't know. I mean, the fact that you have to ask that is the exact reason why you should not care, because it means you won't know. There's no way you could base a strategy on it, so why mess with it? All right, let's take a look at this one. All right, remember where your multiple choice answers are found. Maybe you can check them. Multiple choice answers are here. Right, give it a shot. All right, if you don't have a thing here, let's pick a thing. So let's take a look. You know how the test works. It'll sit there and wait for you. It's a very patient test. It'll wait as long as you want. Gara, please pick the choice from where it's indicated on the screen. Yeah, thanks. Okay. All right, so that's 6 or 7 of you don't have answer choices. Let's pick something. Okay, so let's talk about it. Remember, the point today is alternative ways to solve problems. So, and I mean, what we've been seeing today pretty much so far is things that worked when you were in 5th grade or so. So why spoil it, right? So let's take a look at some way you can do that. I mean, one way you can do this, which works on a lot of rate problems, is just to make a list again. You like making lists, right? So this is 10 revolutions per minute, which means that it's 10 over 60. Yeah, 5th grade method, right? That's 1/6 revolution per second. And then this is 40 revolutions per minute, so that's 40 over 60, which is 2/3 revolutions per second. So we can just make a list. It's how many seconds, yeah, long division. Well, you could do long division. If you really want to do it, you could divide these numbers by long division. I mean, it would give you a decimal, but, if you really wanted to, you could. Yeah, you could use that, right? I mean, it would be kind of more of a pain than it'd be worse, but if long division was your new friend, you could always use it. So let's make a list, right? You have answer choices give you a bunch of times that you can do this at. So let's just do for each time. So choice A is 6 seconds. We can just say, make a list. Choice, so then it's time in seconds, and then year P, and then gear Q. I mean, it helps to make lists like this just so that you don't get lost in the middle of doing the problem. Because it is weirdly likely otherwise that will happen. So, I mean, if this seems like overkill, you should go ahead and make a table like this, just so that you don't forget what you're doing. Because you'd be surprised how easy it is to do that when you're taking a pressure test. It's very easy to forget what you're actually doing midway through. It's weird, but true. So with choice A, that means we're looking at 6 seconds. Gear P is 1/6 times 6, so 1 revolution. Gear Q is 2/3 of 6. What do we want here? What are we looking for in the table? We're looking for what? Yeah, 6 difference is supposed to be 6. This difference is only 3. That's not good enough. I mean, you might, at this point, you may already realize that because they do start rotating at the same time, so you may realize it's twice as long right here. If not, you can just keep making the list. So B is 8 seconds, which means here P goes 8 sixes, 4/3 revolution, and that's 2/3 of 8. This difference is 12 thirds, which is 4 revolutions. Not good enough. C, 1/6 of 10 is this terrible number. It's 5 thirds. It's 10/6. Then it's 20 thirds. So the difference here is 15 thirds, which is 5 revolutions. We're getting close, right? B is 12 seconds. 1/6 of 12 is 2 seconds, 2 revolutions. 2/3 of 12 is 8 revolutions. Difference is 6. We win. I mean, it's still not terrible, right? You can do this. Okay. Don't be afraid to just list out what happens at regular time intervals or whatever. It's doable in the time that you have, and it will exhaust the cases. I mean, if you can find a way to do something like this, and no matter how the problem works, you can absolutely do it. I mean, there's a couple other ways to do it. Let me just outline those for you, and so that we can move on to another problem. But making a list is what I want to drop into your heads today. I mean, a couple more traditional ways to solve this problem. One way to do it is to figure out the rates, which we already did anyway, which is 1/6 revolution per second for, yeah, that's what you're doing. No, that's what I'm going to do right here. 1/6 revolution per second for P and 2/3 revolution per second. It's actually better to leave it as 4/6 like you did, because it's common denominator. So, and then you can just set up an equation. So the equation would be the number of revolutions for Q is number of revolutions for P plus 6. This would be time in seconds times 4/6. And this would be time in seconds times 1/6. And then if you solve this, that'll work. Another way to do it is, that's one way to do it once you've got the rates. And then the other way to do it once you've got the rates is to think relatively. You can think in relative terms, because the point is that gear Q is faster than gear P. Gear Q is faster than gear P by exactly 4/6 minus 3/6, or 1/6 equals 3/6. That's the relative rate. In other words, this is the relative rate, which means that it's the rate at which gear Q is gaining on gear P. Like, it's weird to think of this in terms of circular gears, because circular gears are not going anywhere. But if you had, like, traveling on a straight highway, then that would be the rate that gear Q, that car Q, was getting further and further ahead of car P. So then you can just do 3/6 revolutions per second for, and then just find how long it would take to achieve a margin of 6 revolutions at this rate. So that would be 12 seconds. So those are traditional ways. The main point here, though, is just to put into your heads this idea of making a list, because, hey, you can do it. All right, let's move on to another one. How about that? And this is, give this a shot. All right, it's time to pick something. Let's pick something pretty soon, ladies and gentlemen. I just saw the comment about staying with integers, by the way. So yeah, that would be a thing in that last problem. Okay, let's talk about it. There's still like 4 of you who don't have answers, but you gotta know that you have to pick something. That's about all that I can really tell you about that. You gotta pick an answer. You can't not pick one. Okay, let's talk about this real quick. Let me take the choices away from you for a second. And, all right, there, I took the choices away. What can you tell me about this? Can anybody tell me anything about this in a few seconds? Okay, it's going to be bigger or smaller. So that's like, because, okay, one thing about these problems that's a backup is that's a useful piece of information, is that this is a scale diagram. Because for multiple choice, if it doesn't say not, then it is. It doesn't say not to scale. It's an accurate diagram. Okay, so yeah. You can look at it, let's look at it with your eyes. Okay, so let's see. Peter notes that it's bigger or smaller, but let's see if we can do better than that. I mean, what we can, we can get some sort of estimate of this, right? Like, what would you say this ratio approximately is? Now, you can do better than just saying S is smaller than T. I mean, give me a rough idea, like what percent of T is S? Or, yeah, like I like it's about 1.5, right? It's clearly less than 2 to 1. So T is clearly bigger than S. But also, just as clearly, T is very clearly not twice as big as S. So, which means that this ratio is got to be, that the ratio has got to be more than 1 to 1, but it's got to be less than 2 to 1. Okay, this is not any sort of fanciness, right? This is a very basic observation. It's more than 1 time as much and less than 2 times as much, because we look at it with our eyes. Let's see how that does. See how much mileage we get out of that. Okay, well, I mean, A is not more than 1 to 1, so A is gone. And then let's look at the other choice. Okay, so B, heck no, dude. B is telling you that T is more than 5 times as long as S. So there were a couple of you guys who picked that, but let's be serious for a second here. It's clearly not more than 5 times as long. So let's take a look at the rest of these. I mean, how big is the square root of 3? It's about 1.7. Even if you don't know that, it's less than 2, because 2 is the square root of 4. So this is about 4 to 1.7. Oops, that's more than 2 to 1. Because 2 to 1 would be 4 to 2. Oops, not it. I mean, even if you don't know how big that is, that's less than square root of 3. You should at least know that much. So this is 2 to less than square root of 3. And this is 4 to the ratio of less than square root of 3. This is more than 2 to 1, because this last choice is. Because if it were 4 to 2, it would be 2 to 1, so 4 to 1 point something. I mean, I would just look at it like that. I would say it's 2 to 1 point something. And I don't even care what's after the point. This is 4 to 1 point something. The only thing here that could be the right ratio is that one. I mean, this last one is too big. We're done. You can do it. It's a thing. About that. I mean, you can just look at it with your eyes. I mean, one thing you got to know about this test is they build in. This is not an accident that you can do these things. I mean, they very easily could have written answer choices that would be much closer to D, but they don't do it. The reason they don't do it is not because they are unaware that people can look at it with their eyes. It's because they want you to be able to do that as a backup. Like, that's the thing. I mean, they write problems in order to enable these methods. And you will not see these methods discussed in the official answer keys because they don't want to give the game away. Like, you know, I mean, if people want to use traditional methods all the time, they'll certainly smile and let people do that. But using traditional methods all the time is a lot like paying full price all the time at a store where you can bargain on prices. I mean, you can do it if you want to, and if you have lots of money, then you'll be fine. Like, being very, very good at traditional math is like having lots of money in that situation. You know, like, you don't bargain, and you're so rich that you can afford it. But this is like a problem that you can bargain down all the way to 10% of the price. I mean, it's, you know, it'd be kind of silly not to do it. So, Peter, my best answer to your question there is whatever pops into your head, you should try. You should not ever second guess anything. Don't second guess. This is really important because if you put obstacles in your way, then there will be. I mean, here's your genius statement of the day. When you put obstacles in your way, then there will be obstacles in your way. There. How about that? There's your fact of the day. Take that home. I mean, basically, the best way to think about this question is if you think of something that might work, then try it. And then if you get stuck, quit. And then see if you can try to find something else. That's really all it is. I mean, I wish there were more fancy sounding advice that I could give here, but honestly there's not. I mean, this is pretty much all I can tell you. Same thing, Shauna and Essex. I mean, you don't have to pause. I mean, just do it. And then if you get stuck, quit. If you don't get stuck, then you're fine. I mean, you know, so what are some indicators that you should pause? You don't have to pause. But basically, it's not, you're asking the wrong question. So here's the question that I'm responding to now. It's this one down here. The answer to this is don't pause. The answer to this is just do it. Just do what you have in mind, and then just be very honest with yourself about whether you are stuck. This is where people fail. People fail because they are not honest with themselves about being stuck. Like, they've made no progress for a solid minute or two, and they're still like, oh, I think I'm getting somewhere. Like, dude, no. If you haven't made any progress in the last 15 seconds, you just quit. Doraemon, the answer to your question is right there. How did we know that it's less than 2? How do we know that what is? How do we know that that is? Or how do we know what the ratio was? We know what the ratio is because we looked at it with our eyes. That's how we know. Like, look at the length of this versus the length of that, and ask yourself whether that is twice as long as this. And the answer is obviously no, it's not. It's nothing fancy. It's look at it with your eyes. No, you don't redraw it. Again, I mean, maybe people are not seeing these words in the corner of the screen, but no, you don't have to redraw anything because of this. If it doesn't say, if there's no not to scale warning, then the diagram is to scale. So if you were presented with a different problem that were not to scale, then you would want to redraw it. But then except yes, you can. That's actually the whole point of this whole slide. Is yes, you can use your eyes. You can just look at it with your eyes. So, I mean, the only way that you can't is if you don't have eyes that work. Otherwise, yes, you can. This is the whole point of presenting it. But they don't mention that. Where do they say that? Huh? I mean, are you guys looking at a different slide? They don't say not to scale here. Let's see. They do not say that before all questions. They don't. I mean, think about the fact that they have to warn you that it's not. They have to put a not to scale warning. I mean, think about why they have to have signs that say no U-turn. Okay, they have to put a no U-turn sign up because if they don't put that sign up, that means that you can make a U-turn. So that's what that means. So same thing, if they don't, the reason that they have to put a not to scale warning is that if they don't give it to you, it's to scale. Okay, and here are the exact, just to make sure that we are all on the same page here are the official directions for diagrams. Okay, this is the deal. For multiple choice questions, they actually tell you this. For multiple choice questions, diagrams are accurate by default. They are. It's a thing. Okay, if they are not to scale, they must be marked as such. Now for data sufficiency, it's a different animal. Because for data sufficiency, diagrams can't be to scale. And because there's no such thing as scale in the first place. They can have different shapes. Because the point of data sufficiency is that you don't know things at the start of the problem. In data sufficiency, if you have a diagram, then that could have various different shapes, and so there's no such thing as to scale. But for multiple choice questions, you can trust the diagram. Yes, you can trust it. Very much so. Okay, let's see. They do tell you this, just to make sure you read the directions. I mean, that's not a sarcastic suggestion. I mean, read the instructions and make sure that you understand exactly what you're being presented with. I mean, a lot of people also, like when you take the test on test day, a lot of people don't read the directions, and so they cost themselves time. Like, for instance, one thing that people don't know that could actually save you several minutes is that when you take the test on test day, you don't have to click the stupid little circle next to the choice. You can actually click anywhere on the choice. You can click in the words of the choice too, and that will help you. I mean, that can save you 2 or 3 whole minutes in clicking on 78 different problems. And if you just read the directions, you'll know that. I mean, here it's not a big deal because the answers are short. But if you're doing some sentence correction or some critical reasoning thing, where you can click anywhere on all of those words in the choices, you can save a substantial amount of time that way. So, and if you just read the directions, you would know that. So read the directions, do it, it's a thing. All right, yeah, you should know that. But again, it's not me, nice tip. It's like read the directions, people, do it, read them. They're there for a reason. Okay, let's talk about this with a more algebra-ish sort of thing. Okay, so the deal here is that we've got to give, we got to set these areas equal. So we just need to write some equation that says area of square equals area of triangle. So the area of the square, of course, is not very hard. The area of the square is s squared. The area of the triangle is a little bit of a chore. If you have a formula for this, then you have an advantage here, but if you don't, then you can divide it up and make a 30, 60, 90 triangle with it. So this is going to be half of t. And then notice this is going to be the 30, 60, 90 ratios. If you know those, then you can just tell me that this is t square root 3 over 2. That's supposed to be a 2. But if you don't know that, all is not lost. I mean, you can always do this with the Pythagorean theorem if you don't. If you don't remember these ratios, you can always just set up. You can set up t's half squared plus this squared equals t squared, and you can solve it. So it's not, you know, if you need the ratios, if you know the ratios, it's better, of course. But if not, then yeah. So then the area of the triangle is 1/2 base height, which is 1/2. The base is all of t. It's not just t half, because it's the whole bottom thing. And then t rad 3 over 2. So that looks like it is t rad 3 over 4. And then the t is squared. So there. So you have to set these equal. S squared equals that. If you take the square root of both sides of this, everything is positive, so you don't have to worry about a plus or minus sign or anything like that. So everything's positive, so no plus or minus. So that's S is, just don't be scared by it. The square root of t squared is t. The square root of 3 is the square root of the square root of 3, and then that's 2. So then if you divide by t, then you have s over t equals the square root of 3 over 2. So there. The thing. The square root of 3. I mean, even if you don't know it, process of elimination says that this is this. The square root of 3 is the 4th root of 3. And if you can practice your roots, you know, just look up some roots practice on the internet if you need some, you know, that sort of thing. But so therefore, the opposite is true. The upside down ratio is what we want. So we want it to say t to s is 2 to square root 3. And there it is. But again, that's not the point of today's presentation. The point of today's presentation is that you can look at it with your eyes. You can do it. So, again, there are a lot of problems on this exam where there are these very low to the ground kinds of methods that solve them. There are a lot of them. It's definitely a thing. So, and remember, Angelica and others, Angelica, I don't know how to pronounce it. You don't have to take things out of your pocket if you have other things to put in. I mean, you absolutely want to keep everything that will work. You want to be very greedy with solutions, because the more ways you have to do these things, the better. It's always better to have more approaches. More approaches is always better than fewer approaches. Always, always, always better. Okay, let's do one more super fast. We're going to spill over a little bit, but that's fine. Try this one. The homework. I So I'm confused. This is not a class where you guys have homework. Okay, I'm confused. All right, anyway, here is a last problem here. And that's where your multiple choice answers are found. Okay. Yeah, no timer here, I guess. Let's not take a terribly long time on it. Because we're technically over time here, so we'll quit. Okay, let's kill it. There's still about 8 of you who don't have answers, so let's go ahead and pick something. All right, remember today is alternative solution methods day. Let me know how we're going to talk about doing this. How's Ron going to do the problem? Yeah, I'm just going to do out the arithmetic. I mean, again, if you don't know exactly how this works with exponents, then, let's just do arithmetic. Okay, so this is 2 times 2 times 2 times 2 times 2. Looks like that's 4 times 4 times 2. It's 16 times 2. It's 32. And it's 2 to the 5th. And then this is 3 times 3, 3, 3, 3. That's 9 times 9 times 3. That's 81 times 3. So that's 243. Okay, my answer is I have 32 plus 32 plus 243 plus 243 plus 243. Let's see what that is. That's 2, 2, 3, 3 is 4 plus 9 is 13. That's carry a 1. It's 12, 9. And it looks like it is 693, 793. Okay, that's not too painful. All right, my answer is 793. That took me about 15 seconds. All right, well, I mean, this is going to end with 5, so that's not going to be 793. 13 to the 5th, I can take one look at this and say, whoa, way too big. I mean, that's 13 times 13 is already 169, and I have to multiply that by, yeah, that's my quote. I have one L on my name, by the way, but otherwise, thanks. This is so big. I mean, it's 169 times 3 more 13s. There's no way that's only going to be, there's no way it's only going to be 793. And then, okay, if you look at these are also going to be, whoa, way too big, holy what. Because, I mean, if you look at 9 to the 5th, that's 81 times another 9. So let's just look at these other guys. So choice C is 2 to the 6th. Well, 2 to the 5th is already 32 from before. So this is 2, 2, 2, 2, 2, 2. And then this is 3, 3, 3, 3, 3, 3. Okay, well, I already found out that that's 32. And I already found out that that is 243. So, sure. That's 64. That's 729. And, oh, look, I win. It's definitely a thing. You can do arithmetic here. There's my answer. I mean, you can use exponent rules here as well. I mean, just as a quick rundown of how that works. You can do that. I mean, if you want to use traditional exponent rules, then that's doable. So 2 to the 6th, I mean, that's 2, this is 2 times 2 to the 5th. And then it's 3 times 3 to the 5th. The point here is to realize that this is going to be 2 to the 1, and that this is going to be 3 to the 1. That's basically the secret to that. So 2 to the 1 times 2 to the 5th plus 3 to the 1 times 3 to the 5th. That's what you have to do to get this to fit into the mold of exponent rules. You have to just make those powers of 1. And then once you do that, that'll give you, you add the exponents together, and that'll give you what you have in choice C. But if you don't come up with that right away, then there is absolutely no shame in just doing arithmetic thing back to grade school. All right, let's kill it. We're over time by a few minutes here, but thank you for attending. I've got a few more of these flexible problem-solving problems in the lineup, so we're going to do some more of it next time. And we will, you're welcome, everybody. What, writing out a big list of prime factors like what? And the prime factors here would be 2s and 3s, right? Is that what you mean? Okay. Maybe you can explain. All right, let's kill the recording. We got more of this to follow in a couple of weeks. But thank you for attending. Good night and good luck.